In this video, we will discuss the various operations of Avl tree in a graphical manner, as well as the algorithms applied to the programs. As we know, the Avl tree is a balanced binary search tree where all the nodes satisfy the balance factor criteria. As continuation of the previous videos on the same topic, let's revise what is balance factor. The balance factor is nothing but the difference between the height of the left subtree and the height of the right subtree. The difference of the height of the left subtree and the height of the right subtree. And the balance factor has to be -1, 0, or +1. Has to fall within the range of -1 to +1. And whenever a node satisfying that criteria, we'll call it a balanced. And whenever a node violating the criteria, we can say it is not balanced. So let's start with an example. Avl tree, as we know, is a balanced binary search tree where all the nodes are balanced. Means all the nodes satisfy the balance factor criteria. Means the balance factor of all the nodes should be either -1 or 0 or +1, should be within the range of -1, 0, and +1, should be confined within these three values, -1, 0, and +1. Otherwise, we have to say the node is not balanced and the tree hence is not balanced. So now let's have an example. Inserting 14, 11, 17, 7, 53, 4, 13 into an empty Avl tree. We have an empty Avl tree. We have to insert these nodes, these elements as nodes into the Avl tree in the order exactly which is given. In the given order, we have to insert the elements. First 14 we have to insert. 17 is higher in value of 14, so it should be inserted as the right child of 14. 11 is lower than 14, so it should be inserted as the left child of 14. Then 7 is less than 11, it should be inserted as the left child of 11. 53 is the highest among all the nodes inserted so far, so it should be inserted as the right child of the highest node inserted so far, that is 17. 4 is the lowest element as compared to all the nodes inserted so far, so it should be inserted as the so far inserted lowest element 7, as a left child of 7, we have to insert 4. 13, let's keep till this point and let's test the balancing of all the nodes separately from as a bottom-up manner. From 4 is balanced because the balance factor satisfies the criteria. The balance factor is 0 minus 0, that is 0, which satisfying the criteria. 7, for 7, the balance factor is 1 minus 0, that is 1, which is also falling within the range of -1, 0, and +1, satisfying the balancing criteria. It is also balanced. 11 is also satisfying the balancing criteria. The height of the left subtree is 2, the height of the right subtree is 0. So the balance factor is 2, so it is not satisfying the balancing criteria. The balance factor criteria is not satisfied in 11, so we have to make balanced. As we can see, as according to the last videos posted on this particular topic, we can see these are left-left imbalance. So for left-left imbalance, we have seen previously there is a right rotation or there is a clockwise rotation. So we have to rotate 11 at the right clockwise as a right child of 7. We have to convert 11 as a right child of 7. Now see, 11 has become the right child of 7 and 4 stays as a left child of 7. So now all the nodes you can see are balanced. All the nodes are balanced because all the nodes satisfy the balancing criteria. 4, the balance factor is 0 minus 0, 0, satisfying the balancing criteria. 11, the balance factor is 0 minus 0, that is 0, which also satisfies. 7, the balance factor is 1 minus 1, 0. 14, the balance factor is the height of the left subtree is 2, the height of the right subtree is 2, so the balance factor is 2 minus 2, 0, also satisfying the criteria. 17 also, 53 also. Then let's insert the last node, 13. 13 is higher than 11, but less than 14 here. So it should be inserted as a right child of 11. So let's insert 13. For 13, now let's check again whether all the nodes are balanced or not. Starting from the lowest node, we have to proceed to the highest node. Now the lowest node 13, let's check it in a bottom-up manner. 13 is balanced because the height of the left subtree is 0, the height of the right subtree is also 0. So the balance factor is 0. For 11, the balance factor is 0 minus 1, that is minus 1. It is also balanced. For 7, the height of the left subtree is 1, the height of the left subtree is 2. So 1 minus 2 is minus 1 for 7, which also satisfies the balancing criteria. For 14, the height of the left subtree is 3, the height of the right subtree is 2, 3 minus 2 is 1, so it also satisfies the balancing criteria. So all the nodes are balanced now. Now, let's insert 12. As we know, 12 is greater than 11 but less than 13. So we can't insert as a left child of 11 because the 12 is higher than 11. And we can't insert as a right child of 11 because 13 is already occupying the space. So primarily we have to insert 12 as a left child of 13 because 12 is less than 13 and also less than 14. So we have to insert as a left child of 13. Now let's check the balancing criteria of all the nodes, balancing status of all the nodes, whether they are balanced or not. We have to test the balancing criteria for all the nodes. 12, it is balanced. 13, 0 minus 1, 1 minus 0. 1 is the height of the left subtree, 0 is the height of the right subtree. Balance factor is 1, balanced. For 11, height of the left subtree is 0, the height of the right subtree is 2. So 11, the balance factor is 0 minus 2, that is minus 2, which is not balanced. So 11 is not balanced. So here 11 is the node. From 11 we can see it is not balanced. 7 is also not balanced because 7 we are having one left child 4 and 4 is the height of the right subtree. 1 is the height of the left subtree. So 3 is the height of the right subtree. 1 minus 3 is minus 2. But let's first remove the imbalance of 11. Then we have to go for 7. For 11, it's a right-left imbalance. As you can say, it's a RL imbalance. So first of all, we have to make it a RR imbalance. We have to rotate right, the 12 and 13. So 12 will be the right child of 11 and 13 will be the right child of 12 in the next step, like this. And then it will be a right-right imbalance. Then we have converted it into a right-right imbalance. Then we have to remove this by simple left rotation of 11, or we can say anti-clockwise rotation of 11 for right-right imbalance. As we have seen in the last videos, we have to go for the left or anti-clockwise rotation of 11. So now just this. Now here, is it balanced? Now see, this is balanced, this is also balanced, this is also balanced, this is also balanced. This 14 we are having 3 is the height of the left subtree, 2 is the height of the right subtree, 3 minus 2 is 1, satisfying the criteria smoothly. So 14 is also balanced, 17 balanced, 0 minus 1 minus 1, 17 is also balanced, 53 is also balanced. So it's balanced. Now insert 8. Where to insert 8? We can insert 8 as the right child of 7. Okay, because 8 is greater than 7. But already 12 is occupying that. So 7 should be anywhere in the right subtree of 7. Where it should be? It should be the left child of 11. It should be inserted as a left child of 11 primarily. Now we have to test the balancing. 8, it is balanced. For 11, it is balanced. For 12, also it is balanced, as we can see. 13 is balanced, but 7 is not balanced. Why 7 is not balanced? Because 7, we are having the height of the left subtree as 1, the height of the right subtree as 3. So the balance factor is 1 minus 3, that is minus 2. So minus 2 is not satisfying the criteria, doesn't fall within the range of minus 1 to plus 1. So 7 is not balanced. How to balance it? First of all, how to balance it? Now, as we have seen this, is a right-left, imbalance, 7, 12, and 11. So we have the right-left imbalance. So first of all, we have to check it. 7 has to be the left child of 12. The 7 will rotate. Suppose this is the thing. The 11 will have to be the right child of 7. Now, is a right-wise rotation. Right child of 11. Okay. So 11 will be the right child of 7. So for this RL imbalance, we have to first make it a RR. So 11 will be rotated clockwise manner. 12 will also rotate in a clockwise manner. So 11 will become the right child of 7. 12 will become the right child of 11. Okay. And the child of 12, that is 13, will become the right child of this. Okay. The child of 13, the child of 12, 13 will remain as it is as a child of 12 itself. So let's check it. First of all, this will become the, now we have to go for the right imbalance. So right. For this right imbalance, again we have to rotate. This is a right imbalance for 7, keeping 11 in the middle. So we have the right imbalance from 7, 11 to 12, this part. So we have to rotate anti-clockwise the node 7, the left-wise rotation. We have to have the left-wise rotation, towards the left. The 7 has to rotate towards the left. 11 will become the parent node. 7 will become the left child. And what will happen with 4? Then what will happen? So 11 will come up. 7 will become the left child of 11. 8 will become the right child of 7, because 8 is already the left child of 11. When 11 will become the parent node and 7 will be its left child, then 8, which is now currently the left child of 11, will become the right child of 7. That is the criteria. Whenever there is a right imbalance, when we rotate this topmost node at the left, the child of the middle left node, the middle node, the child of the left child of the middle node will become the right child. Okay, will become the right child of the rotated node. Okay, the left child will become the right child of the left child of 11. So let's see the thing. 11 has come as a parent node. 12 and 13 are the successively the child nodes. 12 is the child of 11. 13 stays as a child of 12. 7 rotated down has become the left child of 7. 8, which was the left child of 11, has become the right child of 7. And 4 will stay as it is, the left child of 7. So this is balanced. Now we have to remove, we have to go for the deletion. First, we have to remove the 53. The question is to remove the 53. After removing 53, let's check the balance factor of 14. It is now violating the balance factor criteria. Because the balance factor of 14 is 3 minus 1, that is 2, is violating the criteria. So what to do in that case? Now, we have to bring the immediate, whenever 14 is having, okay, it's the 14 is the cause of imbalanced. Okay, it's unbalanced. The 14 is the unbalanced node. So what to do? We have to just see the unbalanced. Why it is unbalanced? So immediate left successor, that is 11. Immediate left successor, that is 11, that will come up like this. So 14 will go down. So we have to check the balance factor. When 14, the root node causing the imbalance. When the root node is causing the imbalance, so we have to just rotate right, and which will become the right child of 11, and 12, the right child of 11 will become the left child of 14, and 17 will stay as it is, just like this. Okay. 12 has become the left child of 14, 17 stays as the right child of 14, like this. Now we have to remove 11. 11 is a root. So whenever we are removing this 11 as a root, so now you see in the left, what we have in the previous step, we have made 11 as the root node when 14 is causing imbalance. But whenever root node is to be deleted, then the rule is we have to make the highest the highest valued node in the left subtree as the parent node. So what is the highest valued node here in the left subtree? That is 8. 8 has to be the parent node. So that is a rule. Whenever a parent node is going to be deleted, the highest node in the left subtree will become the parent node. So 8 will become the parent node. And the structure will be like this. 11 is deleted, 8 becomes the parent node. Now it is balanced. Okay. Now when we remove 11, okay, now it's balanced. This is balanced, this is balanced, this is also balanced. This is also balanced, this is balanced, and this is also balanced. Now remove 8. Now we are removing 8. Suppose we are removing 8. What is the highest node in the left subtree? That is 7. That occupies the position of 8, becoming the parent node. Now it creates the imbalanced situation because 7 is unbalanced. Why? Because 1 minus 1, 2, 3. 1 is the height of the left subtree, 3 is the height of the right subtree, so it's minus 2. So what to do? 7 is causing the imbalance, the cause of imbalance. So what to do? Then we have to just the cause of imbalance, and that cause of imbalance is right left. This right left transform, this right left imbalance. So we have to make first right. How to make it? Rotating clockwise. Make 12 as a right child of 7 and 14 as the right child of 12, just like this. Now it's again the right imbalance we have. Then we have to shift, we have to rotate left. Anti-clockwise rotation because it's a right imbalance. 7, 12, and 14, right imbalance. So we have to go for the anti-clockwise rotation of 7. So that makes this one. So this is completely balanced. This is completely balanced. Now, we have, with examples, we have studied the insertion and deletion of the nodes. Now let's go for the program. Let's go for the C program example. The C program through which we can apply the Avl tree, all the operations. As we can see, it is applied through a structure. We have created a structure in C. We have created a where all the basic data members are declared, the pointer variables are declared. Okay, there's a left pointer and right pointer of all the nodes we have. Now let's go for the method. Directly, we have to see the methods. First of all, the inserting method. How a node can be inserted? When a node can be inserted in a Avl tree, then how actually which method is represented by, that is being shown in the code, that is represented by the code given. Now, when t equal to null, if the tree is null, then what we have, the t data, the data of the t, the data element of that particular tree instance, that is t, that is symbolized as pointer t. The t will be t's data part. T is having the data part, the left, the right pointer. The t is a node. T is a node of a tree. A t is a subtree, we can say. T is a pointer that is representing a particular node of a tree, which is by itself a subtree. And the data part of a t is assigned by the x, the value, but we insert, and the left has become null. We have to assign the left as null and the right as null, because we are actually inserting the first node in an empty tree. When t equal to null means the tree is completely empty, completely vacant. We are going to insert the first node. So the left child in the left pointer will be assigned by null. The right pointer is also assigned by null. Otherwise, means if this is not null. If x is the element we are going to insert is greater than the data element of the parent node, tree data is the data element of the parent node. If it is greater than, then the right of t, in the right of t, the node is inserted. The right of t, the node is inserted, and it is recursively called. The insertion is recursively called by t right and x. T right the right pointer of that particular node, that is a right subtree, that will be assigned as a subtree t pointer, means again that subtree will be tested in the next step. And again, if the data is found to be higher than that particular subnode, then again further it has to be inserted at the right subnode. Then again the recursive function will be called, and in this way, so long as x is found to be the higher in value as compared to the right subnode of a particular node, okay, this process will go on, and finally it will be inserted at the right of any subnode, right of the last subnode found so far. So by doing so, if the balance factor is found to be -2 means if the number of left subtree, the value of left subtree, right subtree is too higher than the value of the left subtree, if there are two more edges in the right subtree as compared to the left subtree. So right subtree is having more height, two more height as compared to the left subtree, because we know the balance factor, BF means balance factor, is actually a difference from the left subtree to the right subtree. So whenever the balance factor reaches -2, this means the height of the left subtree is 2 more than the height of the right subtree. So it's a right-right imbalance. Okay. So it is actually the right-right imbalance situation. If x greater than t right data, if x is greater than the t right data, means we are having the balance factor -2, means there are two more edges. There are two more edges are there as compared to the left subtree. So we are having the height of two more in the right subtree as compared to the left subtree. Okay, the difference is 2. Now the element is found to be greater than the right subtree theta, then there will be a right rotation, because it's a right-right imbalance. It's a right-right imbalance. So we have to call the method RR. Otherwise, else means the value is less than the t right. Whatever the element we have in the right part of that particular node, if the element we are going to insert is less than that, this means it should be inserted in the left. So it's a right-left rotation. We have to call RL method that represents the right-left rotation. Similarly, we have otherwise, the else part represents otherwise. If the element we are going to insert is less than the parent node, okay, then T left, the left of that particular node, will have this new node X to be inserted subject to this recursive call. It will go on the left node, the successive left child, it will go to the successive left child as long as this recursive function will execute. So every time it will go to the left subnode till it finds the lowest one, and below which we can insert the element if it is found to be less than the nodes. Whichever nodes we can find is for which the newly inserted element X is less than that will be inserted at the left of that, okay, as a left child of that node. Now, the balance factor, if there are two more height of the left subtree as compared to the right subtree, then we have, and also the element we are going to insert is less than the left child of the particular node, we have the LL, because there is a left imbalance. So we have to call the LL method to run the imbalance method, to run the balancing method to remove the imbalance. So we have to remove the imbalance and we have to run the balancing method by calling LL, because it's a LL imbalance. Balance factor 2 means there are two more nodes at the left, in the left subtree as compared to the right subtree, and the element we are going to insert is less than the particular left subnode. Okay, then we have the two successive left sublevels. So it's a left imbalance. So you have to call the LL method for removing the left imbalance and for balancing. Else otherwise means x is greater than t left. X is greater than t left means x will be the right child of particular node t. So it's a left-right imbalance. To remove the left-right imbalance, we have to call the LR method. LR method. In this way, we can balance the nodes separately and individually. Now, what is LR and what is LL? Now see, rotate right. For any node, this method actually tells us that how the right rotation is done. This node represents the method of right rotation. Whenever a node is rotated right, in two cases, a node can rotate right. When there is a left-left imbalance, LL, then the node can shift right. Or there is a RL imbalance, then the node can shift right, either LL or RL. In case of LL imbalanced, only one rotation required, that is right rotation or clockwise rotation. One right clockwise rotation is required for LL imbalanced. And for RL imbalanced, we require two rotations, in which the first rotation is one clockwise right rotation. We have seen in the previous slides and the previous videos. So in both the cases, what will happen? The left child of x for left-left imbalance or for right-left imbalance, both, we have to assign y as a left child of x, and whatever the right child of y we have, okay, the left child of x is y. The y is nothing but the left child of x. Y is a variable assigned as the left child of x. Okay. And the right child of y means the right child of left child of x will become the left child of x, as we have seen in the previous slides. And the x will become itself the right child of y. So in this way, the particular right rotation or clockwise rotation is performed. These three steps are very important. And then height is adjusted. After that, x's height and y's height, those will be adjusted. Okay. Now the height function is also there, by which it's called again. So now the main process is y is assigned as a left child of x. And then what will happen? The y's right child of y, that will become the left child of x. And x itself will become the right child of y. That is in case of the right rotation. Right rotation takes place in case of left-left imbalance or right-left imbalance. And rotate left is done in case of right-right imbalance and left-right imbalance. For right-right imbalance, only one rotation required, that is left-right, that is towards left, the anti-clockwise rotation. And for left-right imbalance, two rotations are required. One is anti-clockwise and second is clockwise. The first rotation anti-clockwise, that is towards left. So these operations are represented by rotate left. Rotate left function represents the operations where the topmost node is rotated at the left. Okay. Or we can say for left-right rotation, for left-left imbalance, for right-right imbalance, the topmost node will be rotated towards left anti-clockwise. And for left-right imbalance, the lowest node will rotate right, will become the second, and the second node will become the third node. Okay, that's the left rotation. So we can have the rotation left, that is anti-clockwise rotation. In that case, we have the right of x will be assigned as y. Then the left child of y will be assigned as a right child of x. X will be assigned as a left child of y. And the height will be adjusted again. So these are the ways to represent the rotations also. And The LL and RR will be the methods. RR that will call the rotate left, LL that will call the rotate right. Okay. For RR imbalanced, we have the left rotation. For LL imbalanced, we have the right rotation. For LR, we have to successively call for right imbalance, the left rotation, for left imbalance, right rotation. So you have to call successively one after another the rotate left method and followed by the rotate right method. And for RL also, first rotate right method, because for L imbalance, to remove the L imbalance, we have to go for the rotate right method and then followed by the rotate left method. So in this way. So these are the important parts of this particular program we have analyzed. Now to run this thing. First, creating. Enter your choice, 1 to create. Enter the number of elements. Enter the number of elements, suppose 5. Creating a Avl tree, 5. Now insert the data, 34 to 97. Then 11. Let's have these. Okay. Then insert, to insert. Insert another one. First, to display. Okay, print. Now see, in order, first see the in order one. 4, 2, 97, 11. In order. 2, 7, 11, 4, 90. 2, 7, 11. 7 is the parent node of 2 and 11. And finally, 34 is the parent node of the whole tree, is the root node of the whole tree. 34, under which there are two things, like 7 and 90. 34 is a root node, under which we have 7 and 90. Under 7, there are two things, like two nodes, left child 2, right child 11. So 34, we have left child 7, right child 90. 7 is a subtree, parent node of subtree. We have, under which we have the left child 2, the right child 11. So this will be the in order. And pre-order, we know the pre-order sequence will be like this. The parent will be counted first. First, the grandparent, that is a root node. Then the next parent, that is a 7. Okay. Then we have the leaves. Okay. Now we have to insert another node into it. So choice number 2, let's insert a node. Like, for example, insert a node 100. So where to insert 100? Now we have inserted the node 100. Now we have to see it what is the place of 100. See here, the place of 100 is in order. We have see the 90 has become the parent node. 90 has become the parent node, and in 90 we have the 2, 7, 11, 34. We have the 90 and 100. So 90 will become the parent node. 34 and 100 will be there, and 34 we are having the child node. Left child has 7. Okay, and 7 is having 2 and 11. So in this way we have to arrange and pre-order and in order. So now delete. Enter your choice, delete. So let's say we are deleting an element. Which data we have to delete? Suppose, for example, the data we have inserted, those are 90. Let's delete 90. Let's delete 90. Then again printing. We have this. 34 has become the parent node, 7 the root node, and 7 is a second level parent node. Under 34, there are two things, 7 and 100. Under 7, 2 and 11. So we have this. So we have analyzed the insertion, deletion, the rotation functions with the help of C program. In the next video, we'll analyze the other features of different tree algorithms and the practical applications with C or C++ programs. Thank you. Thank you.